Good day, and welcome to the tutorial in Signal Integrity webcast series. This webcast is titled EMI EMC Analysis for High-Speed Digital Designs. It's sponsored by Agilent Technologies. I'm Don Toot. I cover analog and test and measurement topics for electronic design. First, a few words about today's session. If you have any trouble with the console, the first thing to try is simply hitting function key F5 to refresh it. If you need further assistance, click on the yellow help icon below the slides. We welcome your questions. Just type them into the question window on the side of the screen and hit submit. We'll answer as many as possible during the Q&A session that will follow the main presentation, but there's no need for you to wait. Feel free to send in your questions at any time. Today's session is being recorded. It will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides today by clicking the green folder icon on the toolbar beneath the slides. Before we begin, a word about Agilent. Come August 1st, it will become Keysight Technologies. It was announced almost a year ago that the company was splitting. In a week or so, your old Hewlett-Packard legacy test and measurement business becomes Keysight, but it will still be the world leader in test and measurement solutions for wireless communications, aerospace and defense and industrial computers, and semiconductors that you've always known. Let me now introduce today's speakers. Davy Pesort is an assistant professor at KU Leuven in Belgium. He received MS and PhDs in electrical engineering from Ghent University and continued as a postdoc there. Subsequently, he was a research engineer at Agilent EES of EDA in Belgium. In addition to his teaching duties, he's also head of the research group Reliability in Mechatronics and ICT. His current research interests include the development of fast and efficient electromagnetic modeling methods for EMC, SI, and PI, the development of characterization methods for shielding materials and gaskets, as well as the analysis and testing of the mechanical and thermal reliability of electronic modules. He's a senior member of the IEEE EMC Society and member of the International Steering Committee of EMC Europe. In September 2013, he was vice chair of the EMC Europe 2013 Symposium. Now, Hee-Soo Lee, he holds a BSEE degree from Hankook Aviation University in Korea. He has more than 20 years of design and simulation experience in the areas of RF and microwave designs and is currently the application specialist for 3D EM solutions at Agilent ESOF EDA. Now, let me turn things over to him, our first presenter. Hee-Soo, the floor is yours.
Thank you, Don. Hello, everyone. Thank you for joining for this webcast. In the past, EMI EMC problems were considered as a black magic, and still they are. Since there wasn't an easy way to understand and analyze the problems. In the past, using pen and paper with a calculator was the only way, but it has become very, very hard due to increased complexity of the problems. Thanks to advances in numerical analysis technique, it is now possible to analyze EMI EMC behavior before the prototypes are built. Now let's take a look on EMI EMC analysis with the EMPro. So here, what you are seeing is very typical high-speed PCB board that contains the several ICs like drivers and receivers, as well as the grounds, as well as the power planes. And designers need to look at problems starting with the SI, signal integrity problems, where people need to look at the attenuation problems, reflections, and dispersion problems, crosstalk, and the type of problems. Not only these problems need to be addressed, but also PI problem is another problem, such as the voltage drop, switching noise, and crosstalk, and so on and so on. In addition to these SI and PI problems, and EMI EMC problems also needed to be addressed before the product ships. Radiated emission is one of the typical problems design engineers need to be addressed before the design is completed. Looking into the high-speed digital design trends, we clearly see that there is higher bandwidth requirements for the design. For example, 28, 32 gigabit PS SERDES designs, as well as 100 gigabit Ethernet applications. So we clearly see the higher bandwidth requirements. Top of it, traditional design methodology starts to break down. What I meant by traditional design methodology is basically analyzing the old, components of the design, such as PCB, vias, channel, and connectors, as separate components and try to cascade those as parameter blocks. The accuracy of this approach becomes questionable. So people needed to carefully consider where to chop and what to remove, especially for the ground planes and vias. This produced a stronger demand on full EM simulations due to the problems we just talked about: complexity of the design, lack of circuit motors, as well as looking for the higher accuracy of the analysis. So let's take a look on the common numerical analysis technique. In the marketplace, there are 3 prevalent EM simulation technologies. They are all great technologies and very accurate, but unfortunately, none of them is perfect. And these technologies, MOM, which is the 3D planar EM simulation technology called a method of moments, FAM, finite element method, as well as FDTD, finite difference time domain. FEM and FDTD are full-wave 3D EM solvers. These technologies are technically complementing to each other. But however, as I said, unfortunately, none of these technologies are perfect. So you have to choose the right technology based on your applications or needs. However, speaking of the EMI EMC problems, due to the complexity of the problems and 3D nature, full-wave EM solver, which are a FEM, FDTD, are preferred EM simulation technology for dealing with EMI EMC problems. Speaking of the EM solutions, from the Agilent stuff, we offer the 2 design platforms. One is ADS and the other is EMPro. MOM and FAM, these technologies are accessible from the ADS environments, and FEM and FDTD from EMPro. In terms of sharing the design between the 2 platforms, ADS to EMPro layout exporter can be used to send the design from ADS to EMPro. And when the 3D design is built in EMPro environments, the components of 3D design can be added into ADS as a library, so that all the simulations, combination of the PCB structures as well as the 3D structures can be run in ADS environment. When we look at what types of EMI EMC problems are solved within the tool, there are various EMI EMC problems that can be handled in the EMPro environment. First, we can estimate the emission level at specified distance, such as 3 meters or 10 meters, and compare the results against the EMI compliances. Top of it, EMC characterization is one of them. What the tool can do, which will analyze how sensitive the design is in the noise environments. And then coupling analysis, one of the examples shown here that contains the many different boards within this housing, and definitely there are coupling problems between the board to board or cable to cable. This type of problem can be analyzed with the parameter simulation in the tool. And in order to understand what or where is the source of the noise, we can do the hotspot analysis with the near-field analysis capability in the tool. So these are a very difficult type of problems that can be handled in the true EMPro environment. So when we calculate the emission level, for accurate EMI calculation, we really need to have correct input sources or noise sources. There are two ways to configure the inputs in the EMPro environment. One is just going with the standard sources. So as you can see here in this slide, there are various different types of sources available: Gaussian, sine wave, step source, and ESD sources. However, there is another way, which is basically reading the data coming from the CSV, comma separated value format. So we can actually bring the measured data or any other waveforms generated from the ADS environment, and then attach those waveforms into the sources in the tool, so that we can calculate the accurate level of emission out of the simulation results. Once the calculation is done, then the calculation needed to be compared to EMI compliances. In EMPro environment, we are supporting the various different type of EMI limits. For example, FCC Part 15, Class A and B, as well as CISPR 22, Class A and B, and MIL Standard 461. These are typical EMI limits supported in the EMPro environment, so that once the EMI calculation is done, the value of the emission can be compared to against this type of base standards. Now let's take a look on some examples in EMPro. Let me start with the first example, which is a typical chassis. So this chassis example is a very typical type of the EMI EMC problems that contains the PCB structures inside of the chassis. The example board in this example is basically 4-layer PCB structures. And then top of the PCB, we put one of the test differential pair, and the ground plane is actually slotted under this differential pair to see how much of the emission is produced based on the slot on the ground plane. We can start with the emission test by putting the differential signal on this differential pair, and then we can calculate the EMI emission level. So like what you are seeing to the right, a plot on this slide, it shows the EMI calculation results. The green color is the one, the emission level based on the common mode injection to this differential pair with the slot on the ground plane. As you can see, the emission level now is close to the EMI limits, which will be the main source of the problem. Product may be failing to meet the requirements. And then from the EMI EMC behavior, what we could do is putting the plane wave excitation to the design and analyze how much of noise coupled to the certain part of the design. Here in this example, we put the power plane on the PCB, the board, and the blue trace on this slide is showing the how much of energy noise coupled to the power plane on the PCB. But as I mentioned, since we are using the plane wave excitation for this analysis, the noise is represented by the plane wave. So we can see how much of the noise coupled to the structure, and also you show the frequency dependency of the chassis and the PCB structures. Next example is very common example with unshielded twisted pair. For example, like Cat4 cables are USTP. And one of the typical problems with this type of cable is having the common mode on the cable, not having its own ground plane. There is always the higher level of the emission problems with this type of cables. So the analysis was done by putting the differential and the common mode signals to the cable, and calculate the emission level and compare to the EMI limits. So as you can see, green trace is basically with the common signal, the emission level, and differential signal is with the blue trace. As you can see here, it is already over the EMI compliances, which is the typical type of problems EMI EMC design engineers are looking for to understand what is the problem with those cables for EMI issues. The next example is slot on the ground plane. One of the questions people are asking whether a slot really affects the EMI EMC behaviors. The answer is yes. On a typical PCB structure, sometimes it's really unavoidable to have a slot on the ground plane. As shown in this example, a fair amount of energy couples to the slot and start to radiate, as shown in this picture. Radiation shown at the 2.45 gigahertz that frequency. They show that quite amount of energy is radiating from the slot on the ground plane. However, if you look at the bottom picture that shows the differential signal injected, you don't see much of energy coming out from the slot. Is because differential signal is using those traces, not much of the ground planes. So slot is not affecting much of radiation problems, but when the common mode is launched to the pair of the transmission line, then we're going to see much of problems for the emission level. So as you can see to the right side, it shows the emission level at 3 meters. The red is common signal with a slot, which is getting closer to the EMI limits. So next and final example is USB 3.0 signaling. And this is pretty complex design problems. In this case, we were using the 5 gigabit as data rates, so which is shown at the bottom as the source waveform. And the 2 channels for USB 3.0 were basically driven by these signals, and we calculated emission level at 3 meters, which is shown in this plot. Okay, we have seen the various EMI EMC examples. Now we'll discuss how we can improve the design for better EMI EMC performance with several examples. The speaker is Dr. Davy Pitsor from a University of Leuven, Belgium. So Davy, now you have the floor.
Well, thank you, Hisu. So in the next part of this presentation, I will be presenting a few examples that show you how we can use simulation tools like EMPro and ADS to get a better insight in EMC problems. The fact is that real EMC problem is a very complex problem, and in many cases you cannot solve it with brute force. But what we can do is simplify the examples, simplify the structures, and get some real insight into what's happening there physically. We'll be talking about 3 different examples. The first example is called onboard self-jamming. It's an example on onboard self-interference between interconnects and an onboard antenna. The next example is on high-frequency coupling to cables. And the last example is then high-frequency immunity of integrated circuits, taking into account the nonlinear behavior of integrated circuits. So let's start with the first example, onboard self-jamming. What's the background of this example? Why did we start with this work? Well, when you look at a new modern device like a mobile phone, an iPad, and PC, you see that it has many functionalities all squeezed within one single PCB board. And many of those applications are actually wireless and contain onboard antennas. Like, for example, this mobile phone here, it contains GPS, GSM, it contains access to Wi-Fi, to Internet, and all those things are squeezed inside the same small volume, which actually increases the chance for intra-system or onboard interference, here called also onboard self-jamming. This problem was raised as one of the major upcoming EMC challenges at the EMC Europe conference in 2011 in York. So what's the background? Actually, the design of multiple PCB antennas for mobile communications is indeed becoming a very difficult task because there are many possible sources of noise on the PCB. On interconnects, you can have skew, rise-fall time mismatch, delays. You can have reflections. You can have crosstalks between different interconnects. With power integrity, you have switching simultaneous switching noise. You can have direct radiation from components from interconnects. So it is a quite difficult task, but luckily you can make it easier by using simulations early in the pre-layout stage of PCB design. Now so what we want to do in this example, for the interference between interconnects and onboard antennas, we wanted to know what the main noise sources are for that typical problem. And if we then know the main noise sources, how can we reduce the noise coupling? And how can we make the communication link both on board as with the antenna? How can we make it more immune to those self-interference, onboard self-interference problems? Simulation tools that we used in this example are EMPro, where we more specifically use the FDTD solver, where we made extensively use of the possibility of using GPU acceleration. So the examples I will be showing here, for every test case, it took about 2 or 3 minutes to simulate the test case. And we then also used ADS schematic to do more post-processing on the results. So basically in EMPro, we had, for example, S parameters. In ADS, we added extra circuitry to that example. What are the challenges in designing PCB antennas? Well, PCB antennas need to be small in size because they have to fit, for example, inside your mobile phone. At the same time, they have to work at multiple frequencies, so they not only have to work for GSM, but they also have to work for Wi-Fi, for Bluetooth, for GPS. And they need to have a high sensitivity because of the low signal values that need to be successfully received. Now, because of the fact that PCB antennas are small in size, the antenna itself is actually only one part of the antenna. So the onboard antenna typically is some kind of dipole antenna, where the second part of that dipole antenna is actually the ground plane of the PCB itself. This has two big consequences. First, on the behavior of the antenna itself, is that the shape of the ground plane and the size of the ground plane affects the antenna performance and also affects the resonance frequencies. It also has important consequences for EMI, and more specifically for the onboard interference, is that the antenna, because the ground plane is the second part of the antenna, it will induce currents, which we will be calling antenna currents, over the total ground plane. And this also means that unwanted noise coupling can actually happen with things that are quite far from the antenna. And as we will see and prove in this example, is that the unwanted noise coupling is caused or can be estimated by just looking at the overlap between the antenna currents and the return currents of the interconnects or of the components. Looking into the self-jamming problem between interconnects and antennas in a more detailed way, we have to recognize that it's actually a two-way issue. An antenna can be receiving, an antenna can be transmitting. In both cases, we can have self-jamming problems, but they're a little bit different from nature. When the antenna is receiving, what's happening then? Well, the antenna and the RF circuitry that follows on the antenna needs to be able to process very small incoming signals. This also means that any noise that would be induced at the antenna port reduces immediately the sensitivity of the whole receiving circuit. So in this case, when the antenna is receiving, we have to watch out for coupling from digital interfaces, from interconnects to the antenna. When the antenna is transmitting, it's probably transmitting with an output power that can be quite high. So if you just look at GSM, typical output power or maximum output power that is allowed for GSM is 2 watt. If you look at the 50 ohm antenna and we calculate what 2 watt means, you see that you have 14 volts at the port of the antenna, which is quite high. And that also means that there can be quite some coupling from the antenna to digital interfaces. So the way of looking at the coupling in receiving and transmission is actually opposite. When receiving it from the interconnects to the antenna, when transmitting it from the antenna to the digital interfaces. Now, what did we want to do with this example? We want actually to know what's the best location to put an interconnection on your PCB. So what do you see here in this example? You see here a PCB with at the top left representation of an onboard antenna. And then we have 5 interconnects. And we actually wanted to know what's the best position to put this digital interface. Is this position 1, very close to the antenna? Is it position 3, as far away as possible from the antenna? Or is it position 2, somewhere in the middle of the PCB? Now, based on your intuition and based on the normal rules that you know about EMI, namely that distance or separation is most of the time your friend and reduces the coupling, you would think that position 3 would be the best position to put the interconnects. Now, this way of thinking is a little bit misleading, and you will immediately see why if you just look at the antenna currents that are induced by the onboard antenna in the ground planes. They are shown here in the picture in the middle for 960 megahertz, which is the first resonance frequency of the antenna. What you see here is that also in position 3, so at the bottom right corner of the PCB, that you see quite some currents being induced, which also means that there can be quite some high coupling to that position. If you look at the return currents of the traces, well, they just, in this case, with the full ground plane, behave like we expect. For high frequencies, the return current is immediately below the interconnect. So for clarity, from the 5 interconnects in this picture, we only excited 1, the second one from the left. So what we saw then when we investigated this problem is that the overlap between the antenna and the return currents is an indication of the noise coupling, and this can be easily visualized with full wave simulations early in the design process. What is shown in this picture is actually the coupling expressed as an S parameter and S1 parameter from the ports of the interconnects to the port of the antenna for the interconnects in the 3 different positions. What we see that is in position 1, close to the antenna, we get, like expected, the highest coupling from the interconnects to the antenna, going up to minus 35 dB. In position 3 is a little bit less, but not as much as we would expect. So we go down with about 5 dB to minus 40 dB. While in position 2, the middle of the PCB, we get a coupling that is the lowest, which is minus 45 dB. It's 10 dB lower than in position 1. This agrees with what we saw just a minute ago with how the currents flow inside the ground plane. We can prove even more that indeed, looking at the antenna currents in the ground plane, that we can get an idea about how strong the coupling is with respect to the coupling. So what I'm showing here is the coupling from the interconnects to the antenna. At 960 megahertz, we have a maximum. And the interconnects were in position 1, so very close to the antenna. Indeed, what we see is that we have high currents close to that antenna. When we look at 1.17 gigahertz, we actually see a minimum. And indeed, what we see here, if we look at the antenna currents in the ground plane, we see that we actually have no currents induced in the ground plane. It's also a frequency where the antenna is actually not resonating at all. When we look at 2 gigahertz, we get again a very high coupling between the interconnects and the antenna. And again, what we see is that the currents in the ground plane are spread all over the ground plane and are very high in the position where the interconnects are. So this proves that looking at the currents in the ground plane and how they overlap with the the return currents of the traces gives an indication about how strong the coupling is. We can turn this also into the time domain. So what we did here is that we exported from EMPro from the 3D simulation S parameter describing the coupling between the interconnects in the antenna. And we then imported that into ADS schematic, and added circuitry to the antenna. So what we did is that we applied at the interconnects, we applied a quasi-random bit pattern of 2 gigabits per second, and then we looked at the time domain signal that we see at the antenna side. Now what we see here is that for position 1 and position 3 we end up with about the same level of noise, around 15 millivolts, while at position 2, where we had the least coupling, we see a noise level of only 5 millivolts, which is in agreement with what we saw in the S parameters. We can also do the opposite in ADS schematic, so we can also excite the antenna and then look at what's happening in the interconnect. So what we did here is that we applied at the antenna port a sinusoidal signal of 900 megahertz, so a GSM signal, representing an antenna that is radiating with a radiated power of 2 watts. And then we applied at the same time a quasi-random bit pattern at the interconnects. We applied it to the interconnect somewhere at the bottom, and then we looked at the signal at the other side of the interconnect. Now the blue curves that you're seeing in position 1, 2, and 3 are actually the curves that you see when the antenna is not excited at all. The red curves is the signal that you get when the antenna is excited, and you see that you get quite some strong coupling from the antenna to the digital interfaces, where again in position 1 and 3 they're about at the same level, and in position 2 they're much smaller. This also means that in position 1 and 3 the opening of the eye diagram will be much smaller due to the coupling with the antenna than in position 2. Again, all confirming what we saw before. Now let's go a little bit further and look at what happens when we start to when we have some discontinuities in the return current part of the interconnects itself. So Hisu already talked about the influence of slot. So now what happens when we put a slot underneath the interconnects? That happen two things. Well, first, the slot will also influence the antenna currents. What we see is that the antenna currents are pushed more inwards because of that slot. But that's not the only thing. The second thing that happens is that the return currents of the interconnects also changes, and that they are also pushed much more inwards to the ground plane and spread more over the ground plane. So again, what we do here in the picture of the right is only excite one of the 5 traces, but what we see is now, because of the slot, the return current is not only under that trace, but is actually underneath all the traces and even further than that. So what we see is that we get a higher overlap between the antenna currents and the return currents of the traces. And that is also expressed in the S parameters, which are now, we see about an increase of 15 dB in coupling, up to minus 20 dB. We can also see this in the time domain. So when we look at the coupling from the digital interface to the antenna, we see that we get up to levels of 60 millivolts, while for the coupling from the antennas to the digital interfaces, we see quite a high coupling in red here, probably almost closing our eye diagram. Now, based on this, you would think, well, you can solve this issue by just trying to get the antenna currents away from the area where the interconnects, and you could think that you could do that with just placing some guard ring around the interconnects. But that's again wrong reasoning, because we have to deal here with high frequency, high speed effects, and actually the ring can be resonating together with the antenna, and actually the antenna currents will move inwards to the region that's inside that ring quite easily, because it's high frequency. The ring doesn't influence that much the return currents of the trace, but again, we can see that we probably will have a higher overlap between the antenna currents and return currents and with solid full ground plane. Again, this is expressed in the coupling, where we see about, on average, a 10 dB increase in coupling compared to the full ground plane. Now we can then, this was all on a simplified example. You can also do that on a more complicated example, on a real PCB, where you have ground planes which are very often full of holes, openings for components, for vias. And we just compared here what the difference is between if that ground plane would be a full ground plane and a real ground plane. And you can see at the bottom what the difference will be just for the coupling from the interconnects to the antennas. For the full ground plane, we're almost seeing no noise, while for the real ground plane with all the openings, you can see quite a significant amount of noise. So the key learnings from this example is that the coupling between the traces and antenna current spots is one of the main contributing factors of noise. So during the placement stage of components on the PCB, you have to carefully select the locations where you put the digital interfaces. Designs can be simulated and optimized by placing digital interface components outside of regions of crowded current distributions and return path discontinuities, and really need to avoid any return path discontinuity to prevent large current coupling. If you want to read more about this example and the theory behind it, the reference at the bottom of the slide gives you more information about this. Now let's turn to the second example, which is more of a classical EMI example, and we'll be looking to the coupling to cables, and more specific to the high frequency coupling to cables. So what's the background of this example? So in the last decades, electronic systems working in the gigahertz range have been increasing, and they have both wired and wireless interconnections. Electronic systems still have to work reliably in this changing electromagnetic environment. And that's also expressed into mandatory requirements. So in Europe, for immunity, it's now required to test up to 3 gigahertz, 18 or even 40 gigahertz are expected soon. Typically for both emission and immunity, cables and cable harnesses are seen as a very important aspect. Definitely below 1 gigahertz, and we wanted to know the question, what is now the maximum induced current at high frequencies? Stays it always at the same level? Does it increase? Does it decrease? What happens there? Now if we, what we want to do is we want to find the maximum current for whatever incoming direction of a plane wave excitation. Now if we want to do that, then we want to find the maximal current over all possible incoming directions with the brute force method. That would require an enormous amount of simulations, because we need to do simulation for every possible direction. However, if we use the reciprocity theorem correctly, we can do this with only one or very few simulations. And that's what we did in this example. The tool that we used was again EMPro and the FZD simulator, and the reciprocity theorem was applied by post-processing that was done in EMPro's Python interface. Now what's the reciprocity-based algorithm? Well, reciprocity means that the behavior of an antenna, or an unintentional antenna here, or cable, in receive mode can be fully derived from its behavior in transmit mode. So what's the algorithm? We study with EMPro the cable harness as a radiating antenna. We obtain the far field patterns over a whole frequency range, and we use the Python post-processing to find the induced voltages and currents for the cable harness as a receiving antenna. And now we only need one simulation, namely the cable as a radiating antenna, to figure out all the currents coming from all directions, and that way we can easily find the worst case current. We applied this to a simple example. This is a cable, a wire above a ground plane. So it's a cable at 5 centimeters above a ground plane, where we changed the length of the cable from 50 centimeters to 5 meters. At one end, we kept a fixed load of 50 ohm, and the other end, representing the device on the test, we changed the load from a short, open, and 50 ohm. We had the plane wave falling in from 1 volt per meter, and we let that fall in from different directions. And we then try to find the maximum current over the whole frequency range for at the left side of the cable where the device on the test is. This slide shows the far-field patterns for different frequencies, for very low frequencies up to high frequencies. At low frequencies, we see a dipole-like far-field pattern with not much variation, which means that the induced coupling for every direction would be more or less the same. If we go to higher frequencies, we will see a lot of variation with a follow-up of minima and maxima, which means that at high frequencies, the induced current becomes much more dependent on the exact direction of the incoming plane waves. This picture shows you the induced current and worst case current for the three different loads. So the short, the open, and the 50 ohm. And this for three different lengths of the cable. So 0.5 meter, 1 meter, and 5 meter. What we see in all cases is that at low frequency, the maximum induced current is more or less constant. And as is like we expect, so the open gives us the lowest current, the short gives us the highest current, and the 50 ohm is somewhere in between. But at high frequencies, we see in all cases that the induced worst case current starts to go down, and it decreases with a slope of 10 dB per decade. So at high frequencies, the contribution of the cables into the induced signal decreases, and this also means that for immunity, the direct coupling to onboard traces and to a purchase in enclosures will be the dominating factor. We applied the same example to a more complicated setup, more representing a typical CISPR-22 setup, where we have a device on a table about 80 centimeters above the ground plane, with then the cable laying horizontally and on the table and going vertically down to the ground. So this will be represented by a metal box representing the device under test, where we had a 50 ohm load where we tried to find the worst case induced current. The wire is presenting the cable, and it goes down to the ground plane, is ended there, terminated there in a 150 ohm load. This slide again shows the far field patterns at three different frequencies, 100 megahertz, 1 gigahertz, and 10 gigahertz. We see the same behavior as before. At low frequencies, we see a dipole-like radiation pattern. At 1 and definitely at 10 gigahertz, we see a much more complicated radiation pattern where we have a quick follow-up of maxima and minima. And again, at high frequencies, the induced current becomes much more important on the exact direction of the incoming plane wave. Here we then see the worst case current for this example. We see again the same behavior. At low frequencies, we have maxima that are more or less constant when we look at the envelope, and then the envelope goes down with a slope of about minus 10 dB per decade for higher frequencies. We also did this exercise for reverberation room conditions, which we can actually do by adding up randomly chosen plane waves. And what we saw here and what we learned is that actually reverberation conditions don't always seem to give the worst case coupling towards the cable. So what are the key learnings of this example? Reciprocity theorem can be used efficiently to find the worst case induced currents with a limited number of simulations. Coupling to cables is one of the main contributors for immunity at low frequencies, but the importance of the coupling to cables reduces for high frequency. Coupling through a purchase in enclosures or coupling to onboard traces will start to dominate. Again, for people who want to know more about this reciprocity-based algorithm to predict induced disturbances on cables, they can read the reference that is shown below at the slide, where you can find all details about this algorithm. We can take the reciprocity-based algorithm even a step further and actually go and use it to study the high-frequency immunity of integrated circuits. And that's the topic of the third and last example. So what's the motivation or background of this example? Both electromagnetic emission and electromagnetic immunity require knowledge and characterization of the whole chain of integrated circuits, packages, printed circuit boards, cables, and so on. Now, complete EMI solution simulation, including all these levels from the IC to the external cable, is still much too complex for whatever brute force simulation tools. Why is that? It has two reasons. The first reason is that it contains features and components which can differ in size and details by several orders of magnitude. So you have the very small ICs and you have the big housings, the big cables and so on. And moreover, you also don't have all internal details of the components. So that's true for integrated circuits, where you cannot get from the vendors all the circuit details of the integrated circuit itself. What you can get quite often is behavioral models of the integrated circuit, which show you the input-output behavior of the integrated circuit. It's also true, for example, for connectors, from which you can get CAD designs, but which only have the mechanical and not all the electrical connections. So how did we use the reciprocity theorem in this example? We used it to extend the classical S-parameter formulation. So we introduced an extended S-parameter formulation which generalizes the classical circuit S-parameter formulation, also including the coupling between circuit ports and incoming or outgoing plane waves. It's again based on the reciprocity theorem, and because it's an S-parameter formulation, it can be easily introduced in circuit simulators to include also external EMFX direct in the circuit level. Because it's an S-parameter, it can also be attached quite easily to all kinds of circuitry. The example that we then used here is a voltage regulator from Alexis Technology. For this voltage regulator, we did have a behavioral model, which is actually described in the paper shown at the bottom of the slide. We put this voltage regulator onto a PCB, connected it to a trace, and through the PCB, a cable of 1 meter length was connected, represented here by that wire. We had two versions of this PCB, namely one with and one without a slot in the ground plane, and then we looked at what is the immunity of the IC within both cases. What we did in EMPro is we did not simulate the IC, of course. We only simulated the trace with the cable, and then we simulated that as a radiating device, and we extracted the far-field pattern, and based on that far-field pattern, we extracted the extended S-parameter formulation and imported that into ADS schematic. And in ADS schematic, we could add both the behavioral model of the IC model, which is connected to one port of the interconnect on the PCB, and we could we could represent the incoming plane wave as just a voltage signal and connect it to the port that is representing the coupling with external EM fields. To the other port of the interconnect, we then connected a DC voltage source, which would actually mean that in perfect conditions, the output voltage of the IC would be constant. And then we changed the magnitude of the incoming plane wave, we changed its frequency, and looked at the behavior of the output voltage of the IC. There's one extra difficulty here, that's that the integrated circuit is a nonlinear circuit. So for the solver in the ADS schematic, we used the harmonic balance to cope with this nonlinear behavior. This picture here shows us the results of the immunity test. So the output voltage of the voltage regulator is under normal conditions 3.3 volt. In specification, it said that it works properly when the output voltage is between 3.2 and 3.4 volt. When we have the IC with the PCB with no slot, we see that we can apply very high levels of incoming fields without actually having an influence on the output voltage of the IC. So it's working quite well. As soon as we have the slot there, we see that we can get the IC out of spec with the incoming plane waves. So this ends this example. What are the key learnings from this example? An extended S-parameter formulation taking into account the coupling with plane waves was successfully applied to the simulation of EMI phenomena. The calculation of the extended S-parameters doesn't increase the computational complexity of the full wave simulation itself. It's only one quite simple simulation. The extended S-parameters can be easily integrated into existing circuit simulators and combined with, for example, behavioral models of integrated circuits. For who wants to know more about this example, the reference shown at the bottom of the slide gives you all the details about the extended S parameters. So with this I end my examples, and Isu, I give the floor back to you.
Okay, thank you, Davey. So, okay.
I'll jump in then.
All right, just give me a... So by this time, you may be very, very interested in the project shown in this webcast. So if you'd like to get any project shown in this talk, please contact your local Agilent field engineer so that you will be able to get those projects. That includes the ADS project as well as the EMPro. And also, some of the content are shown in the YouTube channel. So you can go to the YouTube channel to see those videos. And if you are interested in evaluating the tool, you can download the EMPro as well as the ADS from the link shown in this slide. Okay, now back to you, Don, for Q&A.
All right, Jesus, sorry I stepped on you there to begin with. So a few of you in the audience have already submitted some questions, and we'll jump right into those in a moment. In the meantime, we'd like you to take a look at the pop-up. That's the survey pop-up that has just popped up. Not quite popped up yet. There's the link, and if you can't get to it now, or if you have a pop-up blocker, you can access it directly. So having confused you sufficiently, let me get back to the questions. Part of the confusion is due to the fact that some of the questions are in multiple parts and they came in at various times. However, Agilent is going to go through all of the questions after this webcast ends, and so the questions that you asked will all be consolidated, and you will actually have answers in a coherent fashion. But in the meantime, we've got some questions that are more easily handled. Like here, how would you treat different grounds on the PCB? If you got a digital ground and analog ground, how would you treat them to minimize EMI?
Yeah, Davey, would you be able to answer this question?
Well, the general way that's being put forward in the last years by several experts on EMI, which I also follow, is actually to try to avoid to have different grounds and well, you have to be very careful with different grounds. You definitely have to avoid going over with traces there, and actually you have to try to have only one high-frequency ground if possible. So, for example, typical thing that's being said is you don't actually need a digital and an analog ground because of the fact that return currents try to return immediately underneath the actual signal. You get that separation between analog and digital automatically. So that's the main advice about different grounds on things. There's quite some good literature about this given by Henry Ott and also by Todd Ubing, if you want to know more about this.
All right. We've been talking about both FEM and FDTD. Can you elaborate a little bit more on why we need two solvers and what the strengths of each one is?
Yeah, as I explained during my talk, the nature of the problem is more like a 3D problems, especially like a chassis examples, and these are all 3D type of problems. That's where we need 3D EM solvers, full wave EM solver. Technically, FEM and FDTD are 3D full wave EM solvers. However, based on the different type of problems, either one of those technologies can be used, but typically EMI problems are getting complex and large. That's where we have a little bit more caning to use the time domain engine, where much bigger size of problems can be handled easily than FEM solver. So to answer your question, yeah, 3D nature of the problem, EMI problem, that leads to using FEM and FDTD. But in terms of getting a larger and complex size of the problem, FDTD turns out to be a sort of more like a better choice for the analysis.
Okay, and actually some folks in the audience are surprised to find that Agilent is marketing simulation tools. Is this a new thing?
In marketing of what?
simulation tools, or that's what I'm reading.
Okay. I guess the question is, this EMPro. Yes. The answer is this EMPro tool was in the market probably 7 years now, which is used for a lot of the ARC microwave as for the high-speed digital designs. And also one of the strengths of the tool is being integrated into ADS environment so that there is a seamless design flow between the tool. But speaking of the EMI EMC, we are taking the advantage of having the full 3D engine, FEM and FDTD, and trying to use this engine or technology to solve the EMI EMC problems.
All right. When we use different power planes, is the slot in the power plane an issue for SI or EMI?
Well, it can be definitely a problem if it depends on how you what you route over that slot and how you handle with things that need to go over that slot. So if you need to have different power planes because you have different powers, you have to be very, very careful how you route all the interconnects related to that slot in between. So that's it's always a bad idea to pass with high frequency interconnects over a slot. It then doesn't only have an influence on the EMC behavior, but also directly on the signal integrity behavior, because the slot will also give you reflections, which will end up messing up your signal integrity.
All right. What schematic capture applications are compatible with the EMPro?
To answer the question, the EMPro is basically EM simulators, with the 3D structures that can be drawn in the tool. Also being able to import all different type of the CAD files or formats. But it's not the circuit design tool. So the way we built the tool is having the EMPro integrated into ADS environment, so that the schematic captures can be done in ADS environment. Some of the examples David showed was using the ADS extensively to set up the circuit schematic, but having those antenna simulations or 3D passive simulations that can be done in EMPro, and these designs can be combined and co-simulated. So for the schematic environment is basically in the ADS environment.
All right. What kind of training does Agilent offer to people who want to learn more about EMPro hands-on?
Yeah, that's good. We do offer the various different type of workshop. If people are interested in just EM technologies, understanding the more in-depth level for FAM, FDTD, and MOM, this type of EM technologies. Yeah, we do offer the EMPro workshop, where we really dive into all the technical details of EM technologies and learn about it. Also, we do offer a EMI EMC workshop for high-speed digital design with an EMPro tool. So if you're more interested in just getting the hands-on or understanding the tool better for EMI, EMC, or high-speed is specific, then you can choose the EMI, EMC workshop for high-speed digital designs.
All right. That concludes today's presentation. On behalf of Electronic Design, I'd like to thank you and the audience for joining the webcast today. You're invited to attend our next event in the Tutorials in Signal Integrity webcast series that's titled How to Optimize Your SERDES Design during a pre-layout phase. That's going to happen on the 25th of September. Meanwhile, thank you to Agilent, which is still Agilent until the 1st of August, for sponsoring this event for us today, and have a productive remainder of your day.